Uh, Good evening, Muthu Krishnan.
Yes, ma'am.
Good evening. Let's wait for
Good evening, ma'am.
some more people to join. Welcome, welcome.
Thank you, ma'am.
We will start sharp at 6:05. Okay. I don't want to make you wait also. So the meeting time is 6 p.m. Uh, for whoever wants to join for the interaction session. And it's always welcome and the doubts are welcome. And for those of who cannot join at this time, the video will be made available um, for later viewing. So I would not like to make you wait more than necessary. So let us wait for only till 6:05 p.m. and then we can start with the session. Okay, I think we've waited enough. Uh, Good evening, everyone. My name is Saida Said, and I am one of the TAs for this course. And I'm a research scholar at IIT Roorkee, and this is part of my PMRF program. So this is the second interactive session that we are having. I would like to be, however, where many people may join or may not join or are present. I would like this session to be uh, more interactive. Uh, so, uh, Krishnan, can you tell me if you are at home or at a place where you can be interactive with the session? Are you there, Krishnan? Uh, Krishnan, are you there? Should I wait some more? Okay, okay, okay. Uh, uh, One second. Am I audible now? Uh, am I audible now? Uh, you can unmute yourself and you can tell me. Can you unmute yourself, Krishnan? Can you unmute? Am I audible now? One second. Am I audible now? No. Okay, okay. I don't need to write now. Okay, that's not a problem. So, you will not be able to interact as, okay, you can interact through message if you want. Uh, is that fine? Yeah. Okay. So, this is the second week, and first of all, let me share my screen. Can you see my screen? But how will I see your message? Can you see my screen? Okay. Let let me move on. This is the second week of our interactive sessions, and in the second week, if we recapitulate, you have studied about the. So you have studied about. One second. Uh, Good evening, Vanita.
Good evening, ma'am.
Nice to see you here again.
Thank you,
So
ma'am.
we have not started yet. So I think we can start now. As last time, this session will be quite interactive because I think that we learn both sides, learn more that way. Okay. So as I was saying, that this is the week two. This is the week two, and what you have learned this week is a basic introduction to your foundation, shallow foundation. Uh, and especially what you have learned is the Ragi's theory and um, some alterations, as in it's the dependence on water table. So what we will be doing is we will be solving some problems based on this week's material. Okay, so this is the first problem that we will see. Oh, 1 second. Okay, so a shallow foundation is 0.6 meter wide and 1.2 meter long. Let me draw this foundation for you. It is always a good practice to draw your foundation when solving a question and name the different values on the drawing, because it gives us a visual idea. It basically helps us in visualizing. So let us say this is our shallow foundation and this is our ground level. So the base of the foundation is 1 point, that is okay, that is in the lengthwise, which will be this. The base is 0.6 meter wide. It's 1.2 meter long. So it means that it's a rectangular foundation, not a strip footing that usually we encounter. So it is a rectangular foundation. This is 0.6 and this is 1.2. The depth of the footing is 0.6 meter. Uh, and the soil parameters, let me write here. Phi equals 25 degrees, C equals 48 kilonewton per meter cube, and gamma equals 18 kilonewton per meter cube. Okay, so we have to calculate the ultimate vertical load that the foundation can carry using the Terzaghis bearing capacity theory. Anybody wants to tell me how we should proceed in this? Vanita?
QU is equals to CNC plus
Hmm.
gamma D NQ plus 0.5 gamma B and gamma.
Hmm. So we can write QNQ plus half of B
Okay,
gamma
0.5.
and gamma. Any particular thing about this question? Any thing we would like to uh, any alteration to this formula for this question? See, the Terzaghis bearing capacity theory is for a continuous strip footing. If we want to use it for, say, a rectangular footing or a circular or a square footing, there are certain shape factors that we have to use, and the shape these are same, but the shape factor for rectangular q rectangular is, let me uh, refer from here. Okay, for rectangular footing, we have q u equals c dash nc into, sorry, 1 plus 0.3 b by l plus q nq plus half of gamma n gamma into 1 minus 0.2 b by l. So if you see here, these are if we remove these, and this, it again becomes our uh, traditional Terzaghis formula. But for a rectangular footing, for the shape of the footing, we have to uh, incorporate these shape factors. This may be SQ and this may be S gamma. Sorry, SC, I should say. SQ is 1. SC. This is for rectangular. You can find this in any book. And for circular or square footing,
Ma'am,
we, yes,
in above formula, 1 of gamma into B,
gamma B. Yes.
so
Thank you.
missing B.
Yes, thank you. Okay, so for circular footing, we have QC, sorry, QU is equivalent to 1.3 C dash NC plus Q NQ plus 0.4 gamma B and gamma. And same is for square footing, but here for circular you are taking the dimension D, and for square you are taking the side. Okay, so that is one thing that we have to consider here, that it is a rectangular footing and we have to take in the shape factors. Okay. Uh, Please give me a minute. I am having a little trouble with my. Uh, Please give me a moment. Actually, I'm not using my extended display today, and my pen tablet is. Uh, it has been mapped for my extended display actually. Okay, so this will be okay now. Okay, yeah, that's fine. So that was first point that we had to consider. What is the second point that anybody would want to take care of only in the initial uh, steps of solving? Anything in particular comes to mind? Uh, so when you're solving these questions, first you have to think about what are the assumptions. What are the assumptions in Terzagh's theory? Okay, so what are the assumptions? First thing that is assumed is that first we had to check if df is less than b. If df is less than b, then it is a shallow foundation, and then we can use Terzaghi's theory because it is not applicable to deep foundations in current form. Maybe we can modify the equation and then use it for deep foundations, but that is for further reading. But in this current form that we have, we cannot use this equation for a deep foundation. So the first thing that we need to see is our df less than b? And we can see that df is less than equivalent to, let me say, less than equal to. So here our df is 0.6 and our b is also 0.6. So we can use this formula. The second assumption, the second assumption is that it is for this particular QU is equal to CNC plus QNQ plus half of B gamma N gamma. This form of the equation I'm talking about, the assumptions in this form of equation. So this is for a continuous or a strip footing. Therefore, in order to use it for other types like isolated footing, we need to incorporate shape factors. which I have mentioned here. These are the shape factors. These, this 1.3, 0.4, these are the shape factors. Okay. Other thing that we need to consider while using any formula, for that matter, any formula that you have, you should first see what are the assumptions made by the author, and if the assumptions hold true, then only you will use that formula. Okay, so the third thing is that it is uh, valid for general shear failure. So can anybody tell me what the criteria is for general shear failure? What is the criteria for general shear failure? Okay, no issue. I will mention that I'm not going to mention what the theory is, like if you have what kind of soil gives a general failure, what kinds of soil gives a local failure type. But I will mention the values. Okay, so general failure we can have in 1 second. Okay. So you might have seen this graph. You might have seen this graph. Actually, let me share my screen. You just tell me if you can see what I'm seeing. Can you see my screen?
Yes, ma'am.
Can you see this PDF? Can you see this PDF?
No, ma'am.
Okay. I think that is because I'm sharing a window. 1 second. Let me share again. Entire screen this time. Okay. Can you see this PDF?
Yes, ma'am.
Okay. So if you have a relatively uh, very dense, if you have a like loose sand, you will have punching shear failure, then you have local shear failure, and then you have general shear failure. So I'm not able to uh, find it right now, but there was a specification given up to, I think, 40 uh, degrees phi. We can take above 40 degree phi, we take general shear failure because then it is dense. One second. Just give me a moment, let me recheck. Okay. One second. Let me stop sharing for a while. I will refer. Okay. Extremely sorry for this, but I don't want to give you any information that is not correct. So I need to check this again. The file is taking some time to open. Here it is. Okay, it is 28. So below 28 degrees, we will have a local failure. Uh, Let me share my screen again. Okay, so as I said, the third thing that you want to check is if it is a general failure or a local failure. Because this equation is specifically for general failure, and for local failure, you have to make some changes, slight changes. Your C2, let me say, becomes 2 by 3 times the given C dash, and tan of phi 2 that you will take in the calculations will be 2 by 3 times tan of phi dash, which is given. So is this fine? Did you understand what I'm saying? Yes, Vanita?
Yes, ma'am, I understood.
Okay.
Modified values of
Mo
coefficient of friction
yes.
for
Modif
local shear failure.
yes. This we have to take. Then we have to. So these are the things that I want to point out in this question. That the first thing you will check is shape. The second thing you will check is if this is general failure or not, because these are all the assumptions of the Tarzagi's bearing capacity formula. So now let us tackle this question again. Let me take this question somewhere else. Let me take it here. Okay. Okay. So now let us start with solving this question. Let us calculate first the shape factors. So what will be the SC? SC, as I wrote, is 1 plus 0.3 B by L. 1 plus 0.3 B by L, which is equivalent to 1 plus 0.3 into 0.6 divided by 1.2. So how much is this? 1.15. Is that correct? Yes, Vanita.
Yes, ma'am, correct.
Okay. So what is our SQ? From the formula, SQ is 1. And what is our S gamma? S gamma is 1 minus 0.2 B by L. 1 minus 0.2 B by L equals 1 minus 0.2 into 0.6 by 0.2, 0.9. So this will be our S gamma. So for these values of NC, NQ and N gamma, you must already know that you have these charts. Also, you have these formulas. Let us use these formulas for NC, NQ and N gamma and calculate these values. Can you tell me these values after calculation, Vanita? No, first, sorry, home. First, let us uh, calculate the modified values of phi and C. Okay, let me write it as 1.15 here only. Okay, so what are the modified values of C and phi, Vanita? What will be C? Instead of 2, let's write M for modified. Yes, Vanessa. Okay, 2 by 3 into 48. This will be 32. Let's say kPa, and that will be
Pi is equal to 17.26.
okay. Thank you very much. Degrees. Okay, so these are our new values of C and phi. Now let us calculate NC and Q and N gamma. So what is the formula for NC? Let us, okay, I'll write the formulas first. Actually, it's not very, writing is not very good on this. Uh, NQ equals e to power 2 times 3 pi by 4 minus pi by 2 into tan phi dash divided by 2 cos square 45 plus pi by 2. Then NC is cot of phi dash NQ minus 1, and N gamma is 1 by 2 Kp gamma. That is, I'll give you the formula for this. You must know this. Uh, if you don't, let me give you the formula. Pi minus 1. Kp is the coefficient for passive earth pressure, where Kp equals 1 plus sine phi over 1 minus sine phi. Okay. So, anybody can calculate these? Calculate NQ first, Vanita.
Ma'am, I didn't calculate, ma'am. Now I calculate after that. I will tell you, ma'am.
Okay, okay, okay. Uh, I want to enclose these. Okay. Uh, can you calculate? Can you calculate now, or you don't have the calculator? I want to enclose these formulae. Okay. So, okay, let us. I will just write the values here. You can calculate later, and it would be a good practice if you calculate also, and if you compare it with the chart also. You will get the same values from the chart as well as the formulas. The charts are based on the formulas themselves. So the values you will get is are give me a moment. Give me a moment. I need to check the values then. Mm, So the values will be for NC, you will get 15.11, NQ 5.78. One second. NC is 15.11. And Q is 5.78 and N gamma is 3.65. Okay, so these are the NC, NQ, and N gamma values. Now can we calculate the QU? The QU is as we have written here. No, we have calculated these values. It will be SC, CNC plus SQ is 1. So gamma N, sorry, QNQ plus half of B gamma N gamma and S gamma. What is SC, Vanita? Can you tell me these values, Vanita?
SC 1.15.
1.15. C is
C 32.
and C is 15.11 plus Q is basically gamma DF. But which gamma DF is this? One of the assumptions in Terzaghis theory is that above the footing, if our footing is embedded, all this surcharge, all this overweight is not considered. And instead, there is a UDL, we may say, uh, there is a surcharge that is considered here. So this will be equivalent to this footing, which is resting on ground, but it has a surcharge, which will be equivalent to the vertical stress at this point, which is gamma dF. So gamma dF we have, then NQ, which will be, let's write gamma dF. How much is gamma? How much is gamma, Manita? 18. 0.6 half of B gamma into N gamma 3.65. into S gamma, which is equivalent to 0.9. Okay. So can anybody calculate and tell me how much this comes out to be QU? This equals 556.048 plus gamma df gamma nq into 5.78. This is 62.424 plus 0.5 into 0.6 into 0.9 into
Ma'am,
8. Yes.
NQ value 10.65, but
N2
NQ value,
NQ
yeah,
10.65
10.65. I think.
by calculation
Yes, ma'am.
from this formula you have taken phi as 17.26.
Ma'am, no, ma'am. Wait.
Okay, do it again, please. Thank you for your efforts, Vanita. Is somebody else has somebody else joined the meeting? Mm, okay. Let me calculate QU from here. 556.04 plus 62 plus 17.739. Q comes out to be 636.211. Okay. Let me check. Hmm. So this is our QU, but let us check again what the question is asking us to do. The question is asking determine the ultimate vertical load that the foundation can carry by using Taragi's bearing capacity theory. So can anybody tell me how we can go from this ultimate bearing capacity? This is our bearing capacity. How we can go from bearing capacity to load? Yes, Vanita? Okay. So we know that bearing capacity basically is pressure and nothing else. So bearing capacity is force by area. One second. Yes, this will be the load into the area of the footing, which will be QU into 1.2 into 0.6. So our QU will be, one second. Vanita, did you get the answer? I did. This is a problem here. Load by area. So our QU will be QU into area, which will be equivalent to 636.211. 636.211 into 1.2 into 0.6. So the ultimate load that our foundation can carry based on Terzagh's bearing capacity theory is Q U is equivalent to 458. Let us stop here. Kilonewton. So this is our answer. And take care that this is the ultimate load. If the question asked for safe load, what we would do is we would divide this Q ultimate by a factor of safety and we would get the safe load, or QU by a factor of safety, it is the same thing, and then multiply it by area. So here ultimate load has been asked somewhere. If you are planning to prepare for GATE or any other that kind of question, you have to take care what is it that the question is asking. So this was our first question. Vanita, did you get the answer?
No, ma'am.
Still not getting it?
Because of n pi, n q, n gamma values not get to same.
Uh,
Uh,
okay. Let me calculate it. Let me not refer it. Let me calculate it again. Okay. Give me a moment. This e raised to power. First, let me check if I have written the formula correct. Do you have any other reference for this formula? Okay, 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 okay. Yes, 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 yes. There is a mistake in the formula. No, 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 no. This is fine. Thank you. E to power 2 times 3 pi by 4 minus 5 by 2 into tan phi dash divided by 2 cos square 45 plus 5. That is the formula. Should be correct. Let me check. Into 2. Uh, Actually, I don't have my scientific calculator with me and I am traveling. So, Vanita, let us do one thing. Let us not get caught up in the uh, calculations. Let us focus more on the concepts that we can learn right now here. And for this, we can also do one thing. Um, we can take it from the chart. Okay, let us take this from the chart. Okay, we don't have the n value. One second. Value of phi we have, which is 17, almost here. And let us take the dash values. So we will have almost something around a value of 11 maybe we have for NQ dash. No, this is NC dash. NC dash is around 11 from the chart. How much have we taken? Yeah, 15. Okay. Hmm. How much is NQ dash from the chart? Okay, why don't you refer to Vanita? Why don't you refer to the table that has been given in the slides from Professor Vedya? Refer to those tables for the phi value that we have, NQ and N gamma. It's almost zero. Yeah, I think these values, according to the charts, are fine. There may be something that we are not doing right in the calculations. Okay, you can refer to the value given by Professor Bedia. Okay, so shall we move on to the next question now?
Yes, ma'am.
Okay, you can cross-check those values. You can even drop me a message about what you found about them. But let us talk about the second question now. So the first question was based on the Terzaghis bearing capacity formula because, as I said, that was one of the major things that you studied in the week. And the second thing that you studied majorly was the effect of groundwater level. Uh, Obviously, everything was major. What I'm saying is numerical based, what you have studied. So, uh, there's this question. A square footing of side 2 meter. Let me draw this footing here. Okay. So, square footing of side 2 meter is subjected to a centric vertical load, is located at a depth of 1 meter. So, there is a centric load. This depth is 1 meter. Of compacted sand having a phi equals to 35 degrees and a gamma saturated equals to 18. Let me write kPa. Okay, groundwater level is 5 meter below. The ground surface. Assume that the soil above the groundwater is saturated. Okay, so let us assume that gamma saturated is the soil is saturated somehow due to rain or capillary effect or whatever it is, but not due to groundwater. Determine the allowable bearing capacity for a factor of safety of 3. So, Vanita, let us walk through this question. Can you tell me the values? Can you tell me the first thing that we should check here? We see that phi is greater than 28, so this is general failure. That is good. We see that this is a square footing, so we will be using our SC, SQ, and S gamma. Here also we see that is 1.3 and 0.4. But see, why no shape factor for Q is coming out? Because as I told you here, somewhere here, that all of this is converted into a surcharge. And therefore the Q term will not be affected by the shape of the foundations. That is why there is not a SQ in this. So this was, sorry, I forgot again, 1.3, 0.4. Okay, 1.3, and that's 0.4, but divided by, actually into, it's actually 0.8. That is why when it's multiplied by 1 by 2, the whole term becomes, because there is a quotient of 0.5 gamma n gamma b. So 0.5 is becoming 0.4. So the SQ is S gamma actually is 0.4 into 2, which is 0.8. Okay, I hope you understand what I'm trying to say. Not, I don't think I said it very well, but okay. And And can you tell me the NC, N gamma, and NQ for this, Vanita, from the chart? For 35 degrees from the table actually.
NC equals to 46.12,
Mm, yes.
46.12
Mm,
and
and
33.30 NQ.
33.30 is NQ.
NQ. N gamma 48.03.
48.03. Okay, so will you be able to calculate the QU for this? C, C actually is 0. I did not remember that. That's nice. Good for us. One less calculation to do. So this is gamma DF. This will be what kind of gamma will be using? Okay, so the question is saying that our groundwater level is at 5 meter. So will there, let me ask it this way, till how much depth do we see the effect of groundwater on bearing capacity?
3 meter. Below,
Yes, yes,
above the 3 meter, there is no influence.
yes. So this will be our limit actually, B meters below the foundation. B is 2. So total we will have an effect until 3 meters. You are correct. Okay. So for the first part where the level is 5 meter below, will we see any effect of the foundation for of the groundwater? So in that case, let us calculate it directly. Okay. Uh, this will be gamma DF. Gamma is 18 into depth of foundation is 1 plus this will be 0.4 into B into gamma into NQ is, okay, here I did not multiply NQ, into 33.3 into 48.03. How much does that come out to be, Vanita?
The total value is equals to 1291.032.
1291.
291.03.
Let's, it's a big number. It does not, I don't think it needs a point ahead of it. Okay. Give me a moment. Okay. So this is our answer for the first part. Okay. Now the second part. Compare the ultimate net. Okay, one second. What are we calculating here? Allowable bearing capacity for a factor of 3. So this is our ultimate. Let us calculate the allowable bearing capacity first. How much will be the QA? 1291 divided by 3 will be 430. Write it in another color. That 430 kilonewton per meter cube. This is not basically our answer. Our answer is this. Okay. 430.33 actually. Okay. So now let us go to the next. What is the ultimate net bearing capacity? Ultimate net. How do we calculate net? Yes, Vanita. What do we mean by net? Bearing capacity. Anybody wants to answer?
Gross pressure minus original pressure.
Yes. So for our ultimate net bearing capacity, Q and U, we will have to subtract from the Q ultimate the overburden pressure up to the foundation. So this will be gamma dF. Okay, this will be the net ultimate. So let moving forward, what the second part is saying, it is giving us four cases that we need to check the bearing capacity at. Same bearing capacity we have, same foundation we have. The first case was that the, let me draw this with another color. Okay, the first case was that it was situated at 5 meter. Second case is it is at the ground surface. So let us say this is the ground surface. So this is our case 2 at 0 meter. Third case is at the bottom of the base of the footing. Third case is here. Which is 1 meter. And we have a fourth case 1 meter below the base. Let me add a fifth case of 0.5 meter also. Okay. So this is at 1 meter below, which is 3 meters. Let me add two cases for completion. Let it be 2.5 and 0.5 meter. Okay. So we will be computing for these cases. Okay. So the fourth case is 1 meter below. Fifth case is 2.5 meter below, somewhere here. Sixth case is 0.5 meter below, somewhere here. So this is our first, second, third, fourth, fifth, and sixth case. Okay. So how do we proceed with this question? The first case we already did 5 meter below. This is already done. The second case is at ground surface. So our QU basically is gamma dF into n gamma plus half of B gamma n gamma, sorry, NQ. Okay. So any suggestions on how we will get this, Vanita? Any suggestions, Vanita?
At a ground surface, uh, first part and a second gamma cause of
Your voice is breaking. I could not hear what you said. Sorry, I could not hear what you said, but let me go on because I think we will kind of fall short of time. So, as I mentioned that this term is due to the overburden, responsible for effect of this overburden. So, when our water table is moving to the ground surface, this uh, weight is also changing because water is being added. So this term will change, and this term is due to the soil below the footing. And as water table is changing, this term will also add change. So Q and these will be same, but this gamma and this gamma will be different. So our QU will be equivalent to gamma. What will it be equal to gamma? Vanita? It'll be equal to gamma submerged, because I remember in last session I did mention that when we have soil underground, we have a submerged water weight, or submerged, we get a submerged weight, and gamma submerged is just gamma saturated minus gamma W. So we'll have gamma submerged into DF into NQ plus half of B gamma submerged and gamma. Can you calculate this, Vanita?
575.52.
Okay. Based on this formula itself?
Ma'am, off in the place of off, we replace 0.4 because of
Yes,
square
yes, yes,
footing.
yes, 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 yes. Yes, yes. Thank you, thank you, thank you. That is why I love interactive sessions, because otherwise I don't know what mistakes I'm making. Okay, so now coming to the next mm, actually, let me duplicate the slide. Okay. and let me delete this. Okay, this. Oh, this also, and this also. Okay. So the second, the third part here at the bottom, at the base of the footing. This is our third case. So let us go back to our QU. Remember, we have to calculate the ultimate net bearing capacity. Have you calculated the ultimate bearing or ultimate net bearing, Vanita?
Ul-
Ultimate. This is QU.
ultimate. Yes, ma'am.
So for QNU is equivalent to QU minus gamma df. Okay, you can calculate it later. Let us move forward. Okay, okay. Next question on the next part. Okay, so here at the bottom of the base of the footing, our equation again is gamma df nq plus 0.4 b gamma and gamma. Okay, so when my water table is rising here, is there any change in the surcharge or the soil above my footing? Vanita, is there any change?
Uh, Gamma changed, but
Huh?
0.4 gamma submerged.
Where?
First part is not changed, but
Yes,
second part.
yes, exactly. The first part will be changed, not changed, sorry, and the second part will be changed. But here, since the entire second part is changing, since the entire second part is changing, second part nahi, entire soil below the foundation is getting submerged, so we simply replace it by gamma submerged. Likewise, we did in last question, the entirety of this soil mass and this soil mass was getting changed. So we simply, what we did was we replaced these terms. But in fifth and sixth case, we will see that if the soil mass is not entirely changing, how will we find the value? Okay, so can you calculate this? QU as well as QNU.
QU is equals to 908
Hmm?
908.52.
Hmm?
QNU is equals to
Hmm?
314.84.
Good. So this is the answer for part number C. Okay. So let me duplicate the slide again. And delete all this. Okay. So let us come to the part C. No, part D. 1 meter below the base. Initially, in the beginning of the problem, solving the problem, we discussed that the influence of the water table will not be seen below the up up to a depth of B below the foundation. Since the B for our foundation is 2 meters, so this is 1 meter and this is 2 meters. This will be the extent up to which the change due to the groundwater table can be seen. So, since none of the soil masses above, which are actually participating in the bearing capacity formula, are changing, therefore, this will be same as part A. Isn't it, Vanita? So let me go to another slide. Okay, so let us talk about part 5, 2.5. Groundwater at 2.5 meter below ground surface. Let me erase some of this. This is 1 meter and we have a limit up to 2 meters and our groundwater table is somewhere here. What will happen in this case? Now QU equals here gamma df n gamma plus 0.4 b gamma n gamma. Okay, so yes, Vanita, will the first term change?
No, ma'am, first time not changed.
Yes, first term will be the same. And what will happen to the second term?
Second term is changed, ma'am. The formula is
Yes, tell me the.
combined submerged value.
Hmm. So uh, let us calculate the effective stress that we have here. Effective stress due to this portion. Won't it be gamma saturated into uh, how much is this height? This is 2, oh sorry, 0.5 plus gamma
Ma'am,
submerged into 0.5.
2.5. I have a small doubt. 2.5 meter at the below the footing, 2.5 meter. There is no influence At the
Not below
ground
the footing.
surface is
Not below the footing. From here.
from ground surface. Okay,
Yes.
okay, ma'am.
Okay. I included this because below the below ground from here. I included this because it is in under the influence, but not completely also. So this term will be replaced by this term. If this is dW and this is H, then your term becomes gamma bulk into dW plus gamma dash into H minus dW. It's basically what it's doing. What the formula is doing is it's calculating the effective stress due to this portion, which will be equivalent to gamma B, gamma saturated in our case, into dW plus submerged part. So what will be the QU in this case? So it will be the QU, Vanita.
640.32.
Hmm. Are you sure?
Ultimate load is the Q ultimate load is equals to 640.32.
No, see, here, this is which case? This is this case, na? Case 3. The water table is here. What the water table is doing, it's reducing this term. So if the water table was below this, which means that whole of this soil would have taken a gamma saturated value, and the QU for that case should have been greater than this. There is some calculation error. Please check. I'll also check.
Ma'am,
Hmm?
uh, I told you mistake. 1 meter at the 1 meter below the base, the QU ultimate load is equals to 623.16.
Eh?
Ultimate load, yes, ma'am. 623.
Okay. Hmm. And net?
Net to 219. 219.72.
Okay. And what about the next question part?
And this value Q ultimate is equals to 640.32.
And what about QNU?
225.33 kilonewton per meter square.
Okay. So let's go to the next. Okay. Let's go to the next last uh, part.